The Skoda 1.9-litre SDi and TDi diesel engines are two of the most technically advanced lightweight diesels available, offering impressive performance and outstanding economy. Other than the fact that the TDi has a turbocharger and the SDi is naturally aspirated, the engines are virtually identical in construction and operation. This video concentrates on the TDi, as it's the more complex of the two. You'll find additional information in Self-Study Book 16. If diesel engines are new to you, then watch Video 8 first. It explains the principles and looks at the 1.9-litre indirect injection engine of the Felicia. This tape is in 3 sections. Section 1 explains direct injection and looks at turbocharging and intercooling. Section 2 describes the electronic management and self-diagnosis aspects. And Section 3 looks at the engine's mechanical features and the injection pump timing. Section 1. Direct injection and turbocharging. Unlike the indirect injection engine of the Felicias, where the fuel is injected into a separate swirl chamber and the combustion gases must travel into the cylinder, these new engines use direct injection. With direct injection, fuel is injected directly into a recessed combustion chamber in the top of the piston. It's more efficient than indirect injection because combustion occurs totally within the cylinder. Having better combustion, the direct injection diesel consumes about 15 to 20% less fuel than the equivalent indirect injection engine. But in the past, direct injection has had the disadvantages of being more noisy, smoky, and running less smoothly. For these reasons, it's generally been restricted to use in commercial vehicles. However, due to notable improvements in combustion chamber design, fuel delivery, and the use of fully electronic injection control, the engineers have largely eliminated these problems. Efficient mixing of the fuel and air has been achieved by designing specially shaped inlet ports and valves. These generate intensive swirling of the air as it enters the combustion chamber. Combustion is refined further by 5-hole injectors with 2-stage injection. By using 2 springs of different sizes, the injectors deliver a small quantity of fuel at a lower pressure first. This causes a more gentle rise in combustion chamber pressure and reduces noise. Another advantage of direct injection is better cold starting. Because combustion occurs in the cylinder, less heat is lost to the cold metal surfaces than with indirect injection. Consequently, the glow plugs are required only below 10 degrees C and then only briefly. In most cases, starting is immediate. In fact, the glow plug's main function is to reduce noise and emissions by remaining lit for a short time immediately after starting. The glow plugs are longer than those of the indirect injection engine and thus are not interchangeable. The warning light, incidentally, doubles as an engine fault lamp. If it lights while driving, the management system should be checked using the VAG 1552. Turbocharging and intercooling. The additional power of the TDi engine over the SDi is due to the turbocharger and intercooler. The turbo uses the energy in the exhaust gases to compress the intake air required for combustion. Compressing the air forces more into the cylinders, enabling more fuel to be injected, resulting in an increase in power. The turbocharger consists of a turbine and impeller on a common shaft. The exhaust gases turn the turbine and the impeller compresses the intake air. The faster the turbine spins, the more the air is compressed or boosted. In turn, the more the air is boosted, the greater the flow of exhaust gases. and so on. The engine can withstand only a certain amount of boosting, so a control valve, known as the wastegate, is fitted. It's operated by a diaphragm assembly, which is joined by a hose to a solenoid valve. The valve is energized by the control unit and has 3 connections. For simplicity, we've turned the valve around in this graphic. One connection is open to atmospheric pressure in the intake. A second joins to the boost pressure side of the turbo, and the third connects to the wastegate. When the engine is under load and the solenoid is open, boost pressure pushes on the diaphragm and opens the wastegate. The exhaust gases then bypass the turbine unused. The turbine slows down and the boost pressure reduces. Closing the solenoid directs atmospheric pressure to the diaphragm. The wastegate subsequently closes and the boost pressure increases. The control unit monitors the level of boost by a combined pressure and air temperature sender in the intake pipe. Because the solenoid is duty cycle controlled by the control unit, the boost pressure is regulated precisely to suit the driving conditions. The level of boost is regulated to adapt to changing altitudes too, the atmospheric pressure being recorded by a pressure sensor within the control unit. The intercooler fitted between the turbocharger and the inlet manifold works like a radiator. The ambient air cools the boosted air, which becomes hot by being compressed by the turbo. The temperature can be reduced by as much as 50 degrees C. With the cooler air, more oxygen enters the cylinders, which leads to an increased cylinder charge and a further improvement in engine output. The cooler air also helps to reduce combustion temperatures and, in turn, the NOx emissions. NOx is reduced further by the exhaust gas recirculation system. The HC, CO and particulate emissions, on the other hand, are converted into water vapor and CO2 by the oxidization catalyst. Section 2. Engine Management. The TDi and SDi management system is similar to that of a petrol engine. The control unit of the electronic diesel control system, EDC for short, receives input signals from a number of engine senders, analyzes them, and then generates output signals for the actuators. For clarity, we'll explain the actuators first. The fuel injection quantity and the time at which it's delivered are regulated by the injection pump, and that, therefore, is where the principal actuators are located. To appreciate their function, you need to understand some of the pump's working principles. Basically, it lifts fuel from the tank, pressurizes it to about 800 bar, and distributes it to each injector in sequence. The high pressure is produced by the pumping element, which is a plunger inside a cylinder or chamber. The plunger is attached to a disc known as the cam plate. On its rear are a series of lobes equal to the number of engine cylinders, and these rest against a set of rollers mounted on a carrier. When the cam plate turns, the plunger rotates and moves back and forth as the lobes travel over the rollers. Although greatly simplified, the back and forth action creates the high fuel pressure, and the rotary movement distributes the fuel to each injector outlet in the firing order. There's just one injector outlet shown in this graphic. To regulate the fuel delivery quantity, the plunger has a central drilling ending at 2 spill ports. A sliding control sleeve fits around this area of the plunger and forms a seal. During the plunger's forward movement, the spill ports are uncovered and the high fuel pressure at the end of the plunger escapes. In turn, the pressure rapidly reduces and delivery to the injectors ceases. Hence, by moving the control sleeve, the plunger's effective pumping stroke is changed. Moving it to the left allows a shorter stroke. Less fuel is delivered to the injectors and the engine's output is reduced. Sliding the sleeve to the right lengthens the stroke. More fuel is delivered and the engine's output increases. The sleeve is coupled by an eccentric ball pin to the quantity adjuster, which is one of the actuators. The coupling allows a rotary movement of the adjuster's shaft to slide the control sleeve back and forth. For precise and rapid movement, the control unit regulates the quantity adjuster's current by variable duty cycle. In addition to altering the delivery quantity, the time at which the fuel is injected must be altered too, to suit changing engine speed and load. The timing is adjusted by the rollers, which the cam plate is pressed against. By moving the rollers in relation to the cam plate, the start of the plunger's pumping action occurs sooner or later. Turning them in this direction causes the lobes to rise over the rollers sooner and the delivery of fuel to start earlier or be advanced. The roller carrier is turned by a piston and spring assembly. The face of the piston is exposed to engine speed-dependent fuel pressure from within the pump. Therefore, the higher the speed, the greater the fuel pressure, and the further the piston and roller carrier are moved in the advanced direction. The pressure acting on the piston is accurately regulated by the start of injection valve. It's fitted in a bypass channel and is pulsed open and closed by a variable duty cycle from the control unit. When it's closed, increased fuel pressure forces the piston in the advanced direction. Opening the valve reduces the pressure and the timing is retarded. Because the valve is operated rapidly, the injection timing is accurately and smoothly regulated. Also on the pump is the fuel cut-off valve. It interrupts the fuel supply to stop the engine when turning off the ignition. Although its voltage signal originates in the control unit, it's the immobilizer circuit within the instrument panel which ultimately controls the valve. Another actuator is the boost pressure control solenoid, the operation of which we explained in section 1. A similar solenoid valve controls the vacuum supply to the exhaust gas recirculation valve. By opening and closing the solenoid, the control unit regulates the time and the duration for which the EGR system functions. Exhaust gas recirculation lowers NOx emissions by recirculating a proportion of the exhaust gases into the intake to reduce the oxygen content, and in turn, the combustion temperatures. Its operation is dependent on engine speed, temperature and load. Remaining output signals control the glow plug relay and its warning light, and the coolant circuit's auxiliary heaters. The heaters are switched on immediately after starting at air temperatures below about 5 degrees Celsius to shorten the engine's warm-up time. Their operating time depends on the temperature of the coolant and the intake air. 1, 2 or all 3 heaters are switched on depending upon temperature and the voltage at terminal DF of the alternator. The heaters are fed by two relays, one supplying two elements and the other just one. It's simply because of the engine's outstanding efficiency and its development of little waste heat that the heaters are necessary. Now here's something specific to the SDi engine. Because the pressure differential between the intake and exhaust manifolds is too small for effective exhaust gas recirculation, the SDi unit is fitted with an electrically operated throttle valve. Closing it reduces the pressure in the intake manifold to help recirculation. The throttle control device is effectively an additional actuator, which receives signals at the appropriate time from the control unit. Its operation is determined by engine speed and load. To recap then, the EDC system's actuators are the quantity adjuster and the start of injection valve, both of which are inside the injection pump, the fuel cutoff valve, the boost pressure control solenoid, this is replaced by the throttle control device on the SDi engines, the exhaust gas recirculation control valve, and the relays for the glow plugs and the auxiliary heaters. Now let's consider the control unit's input signals. They are combined engine speed and crankshaft position sender, air mass meter, altitude sender within the control unit, coolant temperature sender, fuel temperature sender, combined intake air temperature and boost pressure sender, accelerator position sender, brake and clutch pedal switches, the control sleeve position sender, and finally the needle lift sender of number 3 injector. These last two components provide feedback information for the control unit. We'll now consider each sender in turn. The engine speed sender is of the inductive type and provides the control unit with its principal signals of RPM and crankshaft position. To calculate engine load and for emission control purposes, knowing the quantity of air entering the engine is particularly important. The airflow is measured by a hot film air mass meter. The hot film is kept at a constant temperature by current supplied from the control unit. The intake air cools the hot film as it flows over it, so the greater the flow, the more heat is lost, and vice versa. To keep the temperature constant, the control unit has to supply more or less current, and it's this changing current which is used to calculate the intake volume. To avoid too much fuel being injected at high altitudes, where the air pressure is lower, signals from the control unit altitude sender are constantly monitored. Its signals influence the boost pressure control and exhaust gas recirculation systems to prevent black smoke emission at higher altitudes. The fuel delivery quantity and the time at which it's injected are affected by the coolant temperature. It's measured by an NTC-type sender located here. The density of diesel fuel changes with temperature. Therefore, to calculate the exact delivery quantity, the control unit must sense the temperature of the fuel. It's measured by a small sender found inside the main body of the pump. The combined air temperature and boost pressure sender fits in the intake pipe. Its signal influences the turbo's boost pressure control and the operation of the auxiliary heaters. The position of the accelerator, in other words the driver's wishes, is a decisive factor in calculating the fuel quantity and the time at which it's injected, the boost pressure and the quantity of exhaust gases to be recirculated. The accelerator's movement is recorded by the pedal sender. It's simply a potentiometer which produces a changing voltage signal according to pedal movement. Because of the sender and the fact that the injection pump is totally electronically controlled, there's no mechanical connection between the accelerator and the engine. It's known, therefore, as a fly-by-wire system. The brake pedal switch initiates fuel cutoff when decelerating and eliminates the possibility of braking and accelerating at the same time. The switch also carries out the normal brake light function. A similar switch on the clutch pedal instructs the control unit to briefly reduce the fuel delivery quantity while releasing or engaging the clutch to smooth the gear changes. The two remaining input signals supply feedback information for the control unit. Firstly, the needle lift sender. It detects the start of injection by detecting the instant that the needle starts to lift. A pressure pin at the top of the needle is surrounded by a magnetic field created by a coil of wire. As the needle begins to lift and fuel starts to be injected, the pin causes the magnetic field and the coil's voltage signal to change. From this signal and that of the crankshaft position sender, the control unit calculates the current injection timing and compares it against the specified figure in the start of injection map. If the figures differ, the start of injection valve's duty cycle is regulated to correct the timing. The second feedback signal comes from the control sleeve position sender. It's attached to the top of the quantity adjuster and for reliability is of a contactless type. Its exact operation is covered in the self-study book, but basically it works by a moving arm changing a magnetic field in two specially tapered iron cores. The arm's movement reflects that of the control sleeve, and thus the EDC control unit recognizes the quantity of fuel being delivered to the injectors. Like that of the needle lift sender, the signal is compared against the control unit's injection maps for it to complete its calculations. Corrections to the fuel delivery are made by regulating the quantity adjuster which moves the control sleeve. To summarize, the EDC system receives signals from a variety of sensors. After comparing and analyzing the data, the control unit generates output signals to operate the actuators. In this way, the engine is constantly tuned to meet the wishes of the driver and the demands of the environment. EDC includes an emergency running system too. If a fault occurs in a sender or its wiring, the system uses substitute signals from alternative senders or fixed values where that's not possible. In most cases, this allows the car to continue, often without any noticeable problem. In the event of a problem with the accelerator position sender, the idle speed is automatically increased to 1300, enabling the vehicle to drive slowly. The EDC system includes probably the most comprehensive self-diagnosis facility of any current Skoda, and by using the VAG 1552, the technician can locate most defects without additional equipment. The 1552 functions available are 01 interrogate control unit version, 02 interrogate fault memory, 03 final control diagnosis, 04 introduction of basic setting, 05 erase fault memory, 06 end output, 07 code control unit, 08 read measuring value block, 09, read individual measuring value, and 10, adaptation. On these engines, though, being able to understand fully the measuring block function is especially important for diagnosing problems. And the only way of becoming proficient is to study the repair manual and analyze the readings on a car. There's lots of information available. It's up to you to use it. You'll find it helpful to refer to the self-study book, where the self-diagnosis features are explained in more detail. A point worth noting concerns the final control diagnosis function, which checks the actuators and the glow plug warning light. Unlike previous engines, it must be initiated with the engine idling. It's only after the sequence has been progressed as far as testing the fuel cut-off valve that the engine automatically stops, and the remaining actuators can be checked statically. And when fault-finding, don't always assume that the cause is with the management system. Beneath it is a normal engine, which requires clean filters, good compressions and injectors for it to run correctly. Certainly use the self-diagnosis system, but don't forget the basics.
Pressure pumps on switching off the ignition. On vehicles fitted with an immobilizer system, the valve is controlled by a small electronic unit mounted under the pump. It, in turn, communicates with the immobilizer control unit and ignition key. In principle, the immobilizer system works the same as that of the petrol engines described in a previous video. The fuel system functions we've looked at so far, other than switching off the engine, are controlled mechanically. To meet exhaust emission requirements, however, a proportion of electronic control is inevitably required. The electronic control system takes care of the operating time of the glow plug system, the exhaust gas recirculation system, or EGR as it's known, idle speed increase when cold, advancement of the injection point for cold starting, and the reduction of the injection quantity at higher altitudes. The ECU manages the system and, for calculation purposes, receives input information from terminal W of the alternator for engine speed, terminal 50 of the starter circuit, the coolant temperature sensor, driver's courtesy light switch, engine load potentiometer, the glow plug voltage, and terminal 15 of the ignition circuit. The reason for advancing the injection point on starting a cold engine, by the way, is to reduce exhaust emissions. The injection point is advanced when a solenoid valve on the injector pump is energized. Lowering of emissions is also the reason for reducing the injection quantity at higher altitudes. Simply, the higher the altitude, the lower the atmospheric pressure, which in turn means less oxygen to fill the cylinders. Without some form of compensation, too much fuel would be injected for the smaller quantity of oxygen, leading to black exhaust smoke. The atmospheric pressure is detected by the control unit's integral pressure sensor. When the sensor detects atmospheric pressure below 920 millibars, a solenoid valve on the pump is energized, causing the injection quantity to be reduced, and in turn, the emissions. To reduce the exhaust's HC and CO content, an oxidization catalyst is fitted, details of which can be found in the self-study book. To reduce the NOx emissions, the engine features exhaust gas recirculation. Under certain operating conditions, the system recirculates a proportion of the exhaust gases to lower the oxygen content and, in turn, the combustion temperatures. The system's operation depends on engine speed, load, and atmospheric pressure. The EGR valve is controlled by the solenoid-operated vacuum valve, and the neighbouring valve controls the idle speed increase actuator. The final role the electronic system plays is that of controlling the glow plug circuit. To control the system, the ECU considers the coolant temperature, whether the ignition is on or the starter is operating, and even the number of times that the driver's door has been opened. Incidentally, the glow plug circuit is protected by a 50-amp fuse. The adjacent fuse is for the solenoid vacuum valves. Finally, there's one component whose function we haven't yet explained, the engine load potentiometer. It provides a variable voltage signal depending upon the accelerator's position. The signal is used by the ECU to influence the operation of the idle speed increase, the start of injection point for cold starting, and the EGR system. Adjustment or separate replacement of the potentiometer isn't possible, so do not slacken its mounting screws. Similar to Skoda's petrol engines, the diesel engine's electronic control functions are monitored by a self-diagnosis system, which can be interrogated using the VAG 1552. Once the diesel engine's address word, 41, has been entered, these functions are available. 02, interrogate fault memory. 03, final control diagnosis. 05, erase fault memory. 08, read measuring value block. And 06, end output. When problem solving, it's best to check thoroughly by progressing through all the functions. You're probably already familiar with the 1552's operation, and in principle, its use is no different on this engine to previous petrol engines. But there are just one or two points to note. Although on this particular engine, final control diagnosis can be initiated with the engine running, you'll find it easier to hear components working if it's carried out with the ignition on and the engine stationary. Final control diagnosis checks the function of the EGR valve N18, glow plug warning lamp K29, glow plug relay J52, fuel injection quantity valve N194, idle speed increase valve N177, and the advancement of injection valve N108. If a component fails to operate, then further testing of the circuit must be carried out before condemning the component. For detailed information on all the self-diagnosis functions, including reading the measuring value block, refer to the repair manual. The glow plug relay and warning light are checked in the final control diagnosis function. However, to confirm that voltage is actually reaching the glow plugs, connect a test lamp between earth and the terminal strip. The lamp should light when the relay is energized. If it doesn't and the relay doesn't work either, Then check the simple things first, such as the fuse. There are several ways of checking the glow plugs themselves, depending upon the work which you may be carrying out at the time, so we'll describe all of them. To check the continuity of individual glow plugs, first disconnect the terminal strip from each plug. With an LED-type test lamp connected to positive, touch each glow plug terminal in turn. A defective plug is indicated by the lamp failing to light. An alternative way of checking the glow plugs is to measure their total current consumption. By comparing the current against a table in the repair manual, an indication as to how many glow plugs are working can be made. By the way, if the injectors have been removed, then it's simple to test the glow plugs. First, remove the connector from the temperature sensor. This tricks the control unit into thinking that the engine is very cold, enabling the plugs to operate for longer. When the ignition is switched on, you should be able to see the glow plugs glowing. Remember to refit the temperature connector afterwards and cancel the ECU's fault memory using the VAG 1552. If on removing a glow plug the end is found to be burnt, then it indicates that the accompanying injector is faulty. If the injector isn't repaired, then serious and expensive damage to the piston and combustion chamber will occur. Before removing injectors, clean the surrounding area, particularly the pipes. Absolute cleanliness is essential, as just one small particle of dirt entering the fuel system can damage components. Having unscrewed the injectors, it's always best to test all of them, by the way, lift out the heat shields. The shields, which protect the end of the injector and form a gas-tight seal between the injector and cylinder head, are crushable and therefore must only be used once. So always fit new heat shields and make sure that they're inserted the correct way up. To test the injectors, the VAG 1322 is required. Serviceable injectors produce an even cone-shaped atomized spray without drips. The injector should spray or break at the correct pressure. Pump the handle slowly while watching the gauge. A braking pressure of 130 to 138 bar is correct for new injectors, and the wear limit is 120 bar. Finally, test the nozzle for leaks. Slowly press the lever to maintain a pressure of about 110 bar for 10 seconds. No fuel should leak from the nozzle during this time. If the only defect is with the injector's braking pressure, then it can be adjusted by exchanging the shim of the spring assembly. A thicker shim will increase the pressure and vice versa. However, if the injector's spray pattern is suspect, the nozzle drips, or you're in any doubt about its condition, then always fit a replacement injector. And remember, when overhauling injectors, absolute cleanliness is essential. There's an important safety point to be observed when testing injectors. They must only ever be sprayed into a closed container. Never place any part of your skin near the injector nozzle. The high-pressure atomized spray will penetrate the skin, and the consequences can be fatal. Other than a burnt glow plug, Further indications of a defective injector are misfiring, engine knocking, loss of power, excessive black exhaust smoke, increased fuel consumption, and increased blue smoke on cold starting. A faulty injector can often be identified by running the engine at a fast idle speed and slackening each injector union in turn. A suspect injector is indicated by the revs remaining the same or the engine knocking disappearing. From a routine maintenance point of view, the only items requiring occasional checking are the idle and maximum speed settings and the draining and replacement of the fuel filter. The idle speed is regulated here. Do not on any account turn this screw. Because the alternator is fitted with a freewheel, the engine speed must be measured using the VAG 1767, which records the speed from the flywheel and not by using the 1552. The engine's maximum speed without load is regulated by this bolt, which is covered by an anti-tamper protective cap and seal. To check the setting, briefly fully open the throttle and note the revs. If necessary, corrections can be made by turning the bolt, but remember to replace the cap and seal afterwards. The fuel filter, which requires draining of any water periodically, must be replaced at the recommended intervals. To prevent airlocks after exchanging the filter, always fill it with clean diesel. On occasions, you may also need to bleed air from the pump's inlet pipe by filling it with fuel until all the air is expelled from the bleed screw. If available, a vacuum pump incorporating a small tank can be used to simultaneously fill the filter and bleed the system. And now for one final point concerning the fuel system. For the engine to run correctly, the system must be free of air. Unlike fuel, air is compressible. Air bubbles in the system will cause erratic running and can prevent the engine from starting. A hose which is slightly loose will often permit air to be drawn in without fuel escaping. To help prevent such problems, regularly check the security of the hoses and check that the filter's thermovalve O-ring is not accidentally damaged. Diesel power is a completely new venture for Skoda, and the technology may also be new to you. We hope that viewing this tape and reading the self-study book will help to remove some of the mysteries about an engine which, in principle, has been around, like Skoda, for over 100 years.